Today, I salvaged an LED and its driver from an old bulb, and I find the driver part really interesting. It is a switching driver which drives this LED. It is a non isolated driver, and I like to talk about it. It is a current sensing buck regulator which basically controls the current because the LED should be driven by controlling the current, not by controlling the voltage, because LEDs are current controlled devices. It is meant to be controlled by controlling the current, and this way you can basically set the current to the manufacturer's limit and prolong the life of the LEDs. Otherwise, the LEDs may burn because of overcurrent or high current. So now let's take a close-up look at the board, and I really like the construction of it. You can see the first and important component is the fuse, the bridge rectifier, first and second smoothing capacitor, the inductor for interference filtering, another inductor for buck regulator, then its smoothing capacitor. Now you can see the first smoothing capacitor is removed. This is because I had connected 600 volts to this 220 volts circuit, and the capacitor which was previously soldered just went dead immediately, so I had to change it. And I had the 4.7 UF capacitor, but I didn't had other capacitor or of the same rating, so I just left it as it is. Hope for no explosion. And you can see this chip which does almost everything. So now let's try to power it. So now I'm powering it, and it nicely works. So let's try to draw a schematic of it. Well, I've drawn this schematic, and the schematic makes a lot of sense. There's this rectifier part, and the positive of the smoothing capacitor is directly connected to the LEDs, and there are 23 LEDs, and I don't know the current flowing through it, and they drop around 83 volts together. So there is this chip which does almost everything for us. So let's talk about it. Pin 1, 2 and 3 are connected together. Pin 4 seems to be power pin of the chip. Pin 5 seems to be the switch or switching pin of this chip. Pin 6 seems to be some kind of test pin. Pin 7 seems to be the source or emitter of the high voltage built-in transistor inside the chip. Pin 8 can be some kind of sensing pin and it is related to the current regulation. So how does it work? During the power up, there is very little current flowing through the LED through these high resistance resistor, and they charge this capacitor. When this capacitor reaches some voltage, it turns the chip on and it turns on the internal MOSFET. So what happens is that there is large current flowing through these LEDs, through the inductor, through the high voltage switching transistor, and through this resistor to the ground. And because the voltage is linearly increasing because of this inductor, the voltage on the shunt resistor linearly increases, and there is some reference voltage inside the chip. And when the voltage on the sensing shunt reaches that much level, the MOSFET turns off and the chip makes one pulse. And then when the MOSFET turns on, basically when the MOSFET was on, this inductor would collect some energy, and basically this will be negative, this will be positive. But when the MOSFET turns on, this one will become positive and this one will become negative, and this diode then can conduct. So basically the current would flow from the inductor through the diode through the LED back to the inductor. And this kind of chip is the replica of this famous circuit called the current sensing buck regulator. there is some sensing shunt, some amplifier for it, then there is some comparator, oscillator, latch, and the transistor, and the classic buck regulator topology. So the oscillator produces 1% or less than 1% duty cycle, and it is given to the set pin. So basically the Q output goes high and the MOSFET turns on. When the MOSFET turns on, the current linearly increases because of this inductor. So the voltage on the shunt resistor would linearly increase and is amplified by this differential amplifier. It goes to this comparator. This comparator can compare it to some voltage, some reference voltage, and when the shunt resistor reaches that much level, it resets the latch and the MOSFET turns on. So imagine this is our reference voltage. The current is linearly increasing, and when it reaches that much level, the MOSFET turns on. So I guess you may have understand something. So now let's try to make some oscilloscope measurements. Let's first try to measure the voltage on the smoothing capacitor, and then I will connect the probe to the sensing resistor and the switching pin. Well, I have connected my oscilloscope probe to the smoothing capacitor to measure the voltage on it, and here you can see the line, and here we will measure the voltage. So let's turn on the circuit. You can see the voltage is around 222 or 23 volts. So now let's connect the scope probe to this sensing shunt and the switching pin of the chip. So the ground of the oscilloscope goes to ground, one channel goes to this shunt sensing thing, the shunt resistor, other channel goes to the switching pin. So now I've connected my oscilloscope probe to the switching pin and across the shunt resistor. So let's try to turn it on. It is on now, and the switching signal looks something like this, and here you can see the current waveform. This is the current waveform, and this is the switching signal, and here you can see the transistor is on. Here the energy from the core of the inductor is going back into the LED, and then it makes another pulse, and the frequency seems to be 45 kilohertz. And this is the current waveform or the voltage across the shunt resistor. You can see that it increases and there is some threshold, and when it reaches that much threshold it turns off and makes another pulse here. Well, we know the voltage of the LED, which is 83 volts divided by the rectified voltage, and the duty cycle came out as 37.2%, and the duty cycle in the circuit is also 37%. So it makes a lot of sense here. And if you ask me how to improve it, well, I would say that remove this high resistance resistor, add some auxiliary winding in the inductor, and try to power it from the auxiliary winding from the inductor. And to start it up, you can use a capacitor after the fuse, and then some resistor to power the to start the chip up, and then the auxiliary winding can provide enough power for it to operate, because these resistors are dropping around 242 volts minus 16, or maybe the voltage of the chip. So this was about the video, and thanks for watching the video. I hope you liked it, and I hope you liked my explanation about the current sensing buck regulator. It is the most efficient circuit to drive the LEDs. Thanks for watching the video.